All right, let's go and get started. So I'm all color-coded and whatnot with my announcement slides because today's not a lecture. It's the review because on Friday we have our exam. Ooh, ooh. Celebration. All right, so the only announcement I really have is that we're going to be here starting at 8:30, so be here early. Um, Today, that's all we're going to talk about is the exam. So let's go ahead and get right into it. Now, I guess before we get heavy into the exam review, I guess I ought to pass out your graded homework 3, which that is graded, and that grade's posted. I've got solutions up there, and I've got exam review slides. I will go ahead and say the exam review slides are the one thing I don't post on Blackboard. Just as I figure you got to have at least some benefit for being here, right? So that's the way I look at it. So, all right. Okay, Mr. Adkins. All right, Miss. All right, I will get the sign-in sheet passed out after I pass all this out. Okay, so Miss Bailey. Miss Clark, and let's see. You are welcome. Mr. Conley. Mr. Crookshanks. Let's see. There you go. Whoop. There you go. Mr. Lewis. Mr. Mays. Mr. Mays. Mr. McCracken. Mr. Mitchell. See, I think this is what I need to do. I need to stand here because I'm doing less walking to pass them out. Uh-oh, we got to... Okay. Thank you. Mr. Schaffer. And Mr. Watson. All right. About that, I'm probably not. Just because I'm like a terrible throw. Like, I would be afraid that I would launch it at you, and I'd either hit Mr. Dowdy in the head, or he'd catch it, and then I'd be violating FERPA requirements. So I'm just not that good a shot. So, alas. Well, see, there you go. It curved. All right. I've got the homework 3 solution. If you have not already grabbed that, please do so up here. I've also got the exam review slides. I went through, I think, the broad strokes of this on Monday, but I'll go through at least some of the basics. So on problem 1 was actually really short. The big thing you just needed to be aware of was make sure you've got your FY and your FU correct, your hole diameter, the thickness. Now what I did was this. I assumed that the thickness was 1/2. So I'm looking at a single angle. So I compute the block shear capacity of one of those blocks, and then multiply by 2 at the very end. So that's where I've got the nominal capacity of a block. And then the nominal capacity of the entire section is 2 blocks. But don't forget, what's that? Because the problem was this. See, there's 2 angles. See, there's an angle here and an angle here. Yeah, that was a tricky one on bookkeeping. That was kind of on purpose to be tricky on the bookkeeping. No, what? What? I don't know. No. Your shear area, think. Okay, let me go to the failure path. So here's the failure path down below. Okay, so I'm yanking on this, right? So this is the path right here that's in shear. Not the block. I'm saying this red line right here, that is the path that's experiencing shear. And the gross area in shear is that line times the thickness. Okay? The gross area in tension, hold on for one sec. The gross area in tension would be this line times the thickness. And then subtract the holes accordingly. And again, I used a thickness of 1/2, so that was just for one block, then multiply by 2 at the end. Don't forget phi of 0.75. Yes, sir. Well, I did. That's right here. Hold on, let me erase this. That's what I did right here. Because I'm calculating the capacity of a block. Well, there's one block per angle, and there's two angles, so 2 blocks. You could have done a thickness of 1 inch and just calculated one block and went with it. I just think that's easier. Is everybody all right with that? Any questions? Okay, now problem 2. If you pick the WT 7 by 26.5, I mean, it works, but it's not as efficient. And we talked about this last time. So, you know, you go and if you check the next member down, it will work. Now, I think that what I really want to, I guess, harp on is this. Okay, this equation, AG min, yields a value of 7.11 square inches. And I think one of the conceptual issues that people were wrestling with when they were doing the homework, they say, well, all right, I checked the WT 7 by 26.5 and it works. But then if I go and look at the WT 7 by 24, it violates the equation. So can I not use it? The answer is this right here was a guess. Okay? That is not some codified requirement in code that we must meet. This is just a guess, a series of assumptions that we use at the beginning to start our design. It is not the be-all, end-all. The be-all, end-all, whether or not we have a member that meets requirements, is this right here. Here's our phi PN, there's our PU, and then there's our performance ratio of 0.89. That is what we've got to ensure. And if you look, the next one over, it works. Okay? I mean, the point of this problem was to have to go through and do the iteration. Now, I think what might have compounded the confusion a little bit was maybe what happened on problem 3, because a lot of people looked at problem 3 and they said, all right, I do problem 3 the same way, and I get a C15 by 40, and they said, well, I've got the fracture capacity of 450.7, so that's my resistance, and if I divide 352 into that, I get some crazy low efficiency. Well, that obviously doesn't make sense. Well, the answer to that is, well, fracture is a capacity, but it may not be the capacity. Remember, when you do efficiency, you're calculating your load over resistance, but your resistance is the governing resistance. And if you look at yielding, fracture, and block shear, looking at these values, which one governs the design? It's yielding. Yielding's the one that has the lower resistance. So if you take your factored load and divide by that, that's what's going to happen first, and there's an efficiency of 92%. Okay? Does that make sense? That's the point I really want to get across. I mean, we divided by fracture in our example because that's the one that governed. It didn't govern in this case. Yielding governed. So we wouldn't have known that until we went through and did the calcs. All right, does that make sense? Is everybody okay with that? Everybody good?
Yeah, the WT, did he have to come up with a WT7 by?
That's what I was wanting. I told the TA to be very gentle if people didn't. What did very gentle turn into?
I mean, well, what happened is I came up with a WT8 by 25.
8 by 25?
Yeah.
Should have been WT7.
Yeah. Did it say in the problem you have to use a 7?
Yeah.
Sorry.
No, I mean, what I'm getting at is what.
They thought it was just like I just wrote the wrong number down, but I did an 8. But he gave me all the credit.
You get a pass this time.
8 by 25 was better than 7. Whatever.
But not the 24.
What?
The 24, WT 7 by 24 is lighter.
Well, it's mine's more efficient.
But mine's lighter. If I'm buying per pound, I'm spending less money than you are.
That's probably true.
Yeah. But you did get credit, so my advice would be, like a block or so down, there's a 7-Eleven, and they sell lottery tickets. So I'd go get one. All right. Honestly, I will say this. I'm really honestly most worried that you're doing the design process correctly. So that's really what I'm interested in. All right. Does anybody have any questions on the homework? Because I want to talk a little bit about the exam.
The biggest problem I had with homework was just figuring out the seal angle and stuff, this back-to-back thing.
That's a good question. My advice would be on a block shear calc like that, what I did is I just looked at each angle individually.
Okay.
Think about it like this.
So if you had three individuals, what would the name of them?
Just the L.
L by 4 by 3.5
Ye-
by 1.5?
Yeah, but see, you don't even, I'll be honest, you really didn't even need any properties for the angle. I mean, that problem, the only thing you needed to compute was block shear.
The thickness and stuff.
Well, okay, all right, so what's the name of the angle? So they're L 4.5 by 3.5 by what? So what, all right, the 4.5 and the 3.5 are the lengths of the legs, and the 1/2 is the,
But that's usually the approximate.
not for angles. And maybe I should have cleared that up earlier, but for angles, it's a 1/2 inch.
Okay.
Yeah. I mean, if you go to table 1.7 where you're just looking at each individual angle, one of the things it will not report is a thickness. So, because it really is. They're rolled to be 1/4 inch, 3/8, 1/2. That is a reasonable concern. I could appreciate that. So, but yeah, for angles, it's a 1/2 inch. So. I probably should have cleared that up earlier. All right. Any other questions? Yeah.
How should we go about rounding before we get to the final answer? Because
That's a good
I
question.
get a better efficiency than
Because of rounding?
yeah.
Let me say this. You got a better efficiency just based on rounding, but you really didn't get a better efficiency. In the end, if we're picking the same member, it's the same. You see what I mean?
Yeah, but it prevented me from iterating.
Oh, I see. So you actually calculated and got like 90% is what you're saying. That's a good question. Usually what I do is this. For capacity, like kips, like VPN or so many kips, I usually keep it simple and just say round to the nearest 1/10 of a kip. So if you go in, let's say, like right here, I have here this reported as 264.51, but I'd have been fine with 264.5. You know, I'll be honest, I am using some software to generate these solutions, so it behaves a lot like Excel does. Excel doesn't even think in terms of rounding, it just does the math. So this software is doing the same thing. For hand calcs, I'd be fine with just rounding to the nearest 1/10 of a kip, just going with that. Honestly, the nearest kip probably wouldn't be that big of a deal. I mean, I wouldn't say, oh, it's 264 kips, let's round to 300. Like, I wouldn't do that. But 264.5 or saying 265, that'd be fine. What's that?
300
Yeah.
like around
Close enough for government work, right? Now, the nearest kip or the nearest 1/10 of a kip, honestly, the nearest 1/10 of a kip is probably fine. For moment capacity, the nearest foot kip or the nearest 1/10 of a foot kip, same story. So, sound good? All right, let's talk then a little bit about the exam, because hopefully this slide packet that I'm giving you all really helps out. If you don't have, a set, they're up here, which I've got. First off, I've got like a lot of homework solutions up here. Did everybody get a homework solution for homework 3? I got here. Come on up here and grab that. And then I've got a lot of exam review slides. So if you haven't gotten them, go ahead and come up here and grab them. Now let's talk a little bit about what's going to be on the exam, and hopefully this slide pack will help you out. So the exam will be open manual, obviously, and closed notes. You can't do the exam without the manual. You need the manual. So you can have the manual. You're allowed a formula sheet. I think if you've had me for class before, you know the drill that you can put whatever you want on the formula sheet, just no worked out examples. Just because, and again, I've said this before, but I'll get into it again. I'm not a fan of worked out examples on formula sheets, not for my sake, but for yours. Because if you harp on one particular example, I think you'll know how to do that one. But if I throw a curveball at you, the next one, oh, well, now how do we do this? So you really want to make sure you're writing procedures, relevant equations, things like that. We will start at 8:30, so try and be on time, 8:30, okay? I'll have scratch paper, I'll have a stapler. Just bring your manual, formula sheet, pencil, calculator, all that jazz. Okay, topics. So fundamentals. Make sure that you generally understand the process of structural engineering, bidding, responsibilities of the engineer, the role of the consultant, the role of the engineer, et cetera. We talked about that at the very beginning. Make sure you understand the difference between ASD and LRFD. That was a big one in the beginning. So there's fundamentals for loads. Here we focused on lateral loads. So make sure you understand how to determine base wind pressures at a given elevation. Make sure you can distribute seismic base shear, all that stuff that we did earlier. And make sure you have a basic understanding of gravity loads. I mean, I know we showed all that wind and seismic, but then the rest of the semester we've been doing dead loads, live loads, et cetera. So make sure you at least have a general understanding of that, although in here we focused more on lateral effects. Make sure that you generally understand the properties of steel. You know what a stress strain curve looks like. You know what the difference is between a yield stress and a tensile stress. I mean, that matters. It's kind of what we've been talking about. But obviously the meat of this exam is going to be on tension members. So make sure that you can analyze tension members according to the following limit states: gross section yielding, net section fracture, block shear rupture, and slenderness. Make sure that you can design according to prescribed loadings. And when I say design, I'm designing based on the most economical section. The most economical section, in our case, means the lightest weight. Okay? So there's that. And finally, make sure you can design threaded rods, which it's a pretty plug-and-chug expression, so it's pretty straightforward. Okay, now as for what I provided you in this, I've got wind provisions. So I've got the base wind pressure equation, and I've also got the wind exposure coefficient. I've got the formula listed there. That was sort of the tricky part, I guess, for computing wind pressures on a building. Seismic provisions, you've got your period for your building up top. That's the period of vibration under a given acceleration. And it's just a function of whether or not you got a moment frame or a brace frame. Your seismic base shear is just that response coefficient times the total weight of the building. And then the force on each floor is that base shear times that distribution factor in the bottom left. And then all the parameters that you need to compute that distribution factor are there in that box in the bottom middle. All right, sound good? Okay, now, if you'll notice this review sheet also has the stars on the top right, okay? I've had a few people ask me, what do we need to tab? Well, it's all here, okay? It's all in this. So number one, page 2-10, that's where your load combos are. So if you haven't tabbed that, probably a good idea to go ahead and do so. The big ones to make sure that you understand are 1.2 times the dead and 1.6 times the live, and maybe 1.4 dead if you have a whole bunch of dead load and not a lot of live load. Material and shape properties. So number one, make sure that you've tabbed page 2-48 because page 2-48 is going to have the applicable ASTM spec for different grades of steel. So essentially your FYs and your FUs. If you haven't already tabbed that, you need to go ahead and do so. Excuse me. Make sure that you've, if it hasn't been drilled into your head already, make sure you remember that the Young's modulus for steel is 29,000 KSI. Finally, part one, I would have a few fundamental references or tabs in part one for the shapes. What I have tabbed in mine are W shapes, C shapes, angles, L shapes, and WTs. So that's what I have tabbed in mine. You can tab whatever you want, but that's what I think is a pretty reasonable amount of tabs. I mean, you could put tabs on every single one of them, and you have like 30 tabs at the top, and I don't think that's really going to help you out. So WCs, L's, and WTs, I think that's fine. For tension members, we've got gross section yielding, so VPN is 0.9 FYAG. We've got net section fracture. Phi PN is 0.75 FU times the net area times your shear lag factors, your U values. Now your net area for your bolted connections is your gross area. You subtract out any area loss due to bolt holes, which is the diameter of the hole times the thickness. The diameter of the hole is found by taking the bolt and adding 1/8 of an inch. And then you add any relative stagger factors, S squared T over 4G. Your shear lag factors are found in 16.1-28. So if you haven't tabbed that, you need to go ahead and do so. The big one to understand is case 2. So 1 minus x bar per L. X bar is your connection eccentricity. From the connected face to the centroid, your connection length is literally out-to-out measured distance on your bolts. Exterior bolt to exterior bolt. Slenderness limits, make sure you know L over R has to be less than or equal to 300. Lastly, design expressions. So that top left, that's a pretty common one that we can use. Remember design. Remember, those are based on, that one on the top left, that is based on assumptions, specifically with net section fracture. So it is fine to have a member that violates that a little bit here and there as long as your efficiency on the right is less than 100%. Center equation, R min's got to be L over 300. Make sure you're looking up the right R min. You know, for angles, that's not RX or RY, it's RZ. Okay, so because angles don't exhibit an axis of symmetry about the X and Y axis, they're not symmetric. So you gotta go off the principal axes. It's that whole Moore circle stuff that popped up in deformables. Block shear rupture, we've got our expression there. Don't forget to multiply by phi. Phi is 0.75. And lastly, threaded rod design. Our phi value for threaded rod design is sort of built into that expression that you're seeing right there. There was a lot of algebra that we did to get that 8/3 there on the outside of the square root. But that 8/3 outside the square root has phi built into it, so you don't have to go out of your way to compute it. Just take your factored load, your ultimate tensile stress, plug and chug. That'll give you your required threaded rod diameter. Sound good? That is exam 1. Okay, so what I'm going to do is kind of shut up on the lecture and let you all ask whatever you want. Go. Yes, sir.
Explain how you decide how many blocks there are in block B.
Okay. That's a good question. And the answer, there's, I don't want to say there's no simple way of doing it, but sometimes you can use a little bit of common sense to see which ones would be the best answer. So let me pull up a sheet and we'll look at this. There's my pen. Okay. So the first thing that I would concern yourself with if you're trying to figure out what's the appropriate failure path is this. So I'm going to make up a given connection. Which, by the way, before I get into this, will I make you compute block shear on a staggered connection? The answer is no. Okay, I will not do that. But don't worry about that. You can do it. It's just stagger factors, and it's a lot more bookkeeping, so I'm not really worried about it. All right. So let's say I'm loading this connection. Okay. Now let's make up some bolts. Okay. We'll do 1, 2, 3, 4, 5, 6. Okay. The first thing that you need to do is you need to identify a failure path that surrounds all of the bolts. Now I'm going to draw a failure path and then I'm going to explain why that works. Okay. So let's take this one right here. Now, I'm going to say that this is a viable failure path for 2 reasons. Number 1, it actually has a path in shear and a path in tension. You see that? So this long path down here from here to here, does it make sense that this path is experiencing shear? Like this one right here. Does that make sense? The one going this way? Okay. All right. So that's point 1. Like you actually have to have shear and tension to have block shear. The second, I would say, point that makes this a valid connection is that it, quote unquote, surrounds all the bolts. Now, what I mean by surrounds all the bolts is, okay, let's sort of, let's keep in mind, I've actually got bolts right here. Okay? I propose that if I took the Samurai Sword or lightsaber and cut the plate along this line, okay? I mean, imagine if the plate was a sheet of paper and I took some scissors and cut around that I could separate that plate and the bolts would remain intact. Okay? So, in other words, I can have this. I can have, let's see here. What's the best way of doing it? Maybe something like that. See how that sort of popped off? The bolts remain intact. Okay? Does that sound good? All right. This would not be a viable failure path if I had the same thing and I did this. Like, that would not be a viable failure path. Because think about this. Imagine an easy way of visualizing this. Literally, take a sheet of paper, draw this out, and for every bolt, get a thumbtack and just stick it on a cork board. Okay? Then take a pair of scissors, cut this, cut that off. I propose the paper's still going to hang on there, right? Make sense? Now, do you think the paper is still going to hang on the cork board if I also cut this off? And I cut this and this off? No, in that instance, the paper is going to fall off. Okay? Does that make sense? What time is it? Oh, wow. So you tell me, does that make sense? Okay, so the one up top, that is a possible failure path. This is a possible failure path. Another potential possible failure path is this over here. So, is if I cut this out and that block ripped out. Because again, use the analogy that if it was a sheet of paper and it was on corkboard and each of these bolts were like little thumbtacks. Cut that out, the paper can't stay there. It will fall off. Is that a fair way of looking at it? Does that make sense? I literally just came up with that paper and corkboard analogy on the spot. I think that worked out pretty well. I'm using that from now on. That's a good point. Yes, that is for a single plate. True, but let me also say this. So, all right, I'm using somebody's solution. So, that problem on the homework assignment was an angle, right? I would propose that you could do the same thing by just literally doing that and 3 pins. Now, what's the easiest way of cutting that off? Just doing that. Well, then you'd have just 2 angles, which is exactly what we did on the homework assignment if you think about it, because we were basically computing the capacity of just 1 angle and multiplying by 2. I mean, there really wasn't any complex theory with that. I mean, if I'm yanking on 2 identical tension members, the capacity is just how strong one of them is times 2. You see what I mean? It was the same story on the homework. That's exactly what we did. We just said, here's the capacity of this one, and that's a good point. And in that case, then you'd have to say, all right, let's cut out that, and then let's cut out that. Yeah.
But isn't that what you would do for one of these angle problems because they're bolted together, correct? When you're pulling on it, your block rips out, or it's going to be 2 separate plates bolted together.
Well, I'm saying, okay, you're. Yeah, that's what I'm saying. I'm saying you compute the capacity of 1 and just multiply by 2. We're saying the same thing.
And then in a plate, it ultimately comes down to which failure path you're given.
Well, no, that's not what I'm saying. I'm saying it comes, look, for the plate that I drew up there, I've got 3 different options.
Right.
All of them are viable failure paths. What I'm saying is whichever one has the lowest VRN, that's the one that governs. Okay? Think about it like this. If it takes 300 kips for this to happen, 400 kips for this to happen, and 200 kips for this to happen, this is the one that's going to happen. This is the governing path, all right? Think path of least resistance. I mean, the easiest visualization that I think to extend to this is literally, if I grab one end and I start yanking on it, which is going to happen first? The one that has the lowest VRN. Do you see what I mean? Everybody else all right with that? Okay. And did I ultimately answer your question? Okay. And yours as well? All right.
How many questions are going to be on the exam?
That's a good question. How many questions are going to be on the exam? And it's essentially going to be like all of my other exams. One series of conceptual short answer questions and 3 workout problems. I'm giving you more time on this exam than the concrete exam because this exam requires a lot of lookup, more than concrete does. So that's why you're getting the additional time. And finding the values and getting, I mean, this is a big book. There's a lot of stuff there. So I totally understand that finding the right value that you need can take a while, which is why I'm giving you the additional time. I don't think you really need that as much on the concrete exam because everything's there. The only thing that you'll need on the concrete exam are rebar guides, and I'll give you all of that. So, because that's no big deal. But I mentioned concrete, but let's make sure we're still on steel. So. This is your time, so I really want to make sure you're asking whatever questions you want. So, whatever you got.
So it's whenever we don't know a cross section. Or no, sorry, I think I forgot concrete.
That sounds like a concrete
Yeah.
question. Yeah.
So whenever we do a block shear, will it kind of be like the last part on the homework where you gave us like 5 inches between 2 lines of bolts and you kind of know what block you're going to go off of? You should give us the distance from like the lower.
Well, that's a good point. I didn't give you that distance, but think about it like this. It was a C15, right? So once you designed the section, you'd know the actual depth. And it stands to reason that it's going to be in the middle. Do you see what I mean? So if you know the total depth and you know the center, then you could figure out the top and bottom. Now here's why I didn't do the top and bottom. And this goes into, I guess, my second point in regards to block shear. There are multiple potential failure paths, okay? There's also room for a little bit of common sense, okay? If I had to look at these 3 failure paths, if I had to guess which one is most likely to govern based on these conceptual images, I'm going to say it's the one on the top left, okay? And the reason why I am saying that is because this one rips through the smallest amount of area, okay? You want a conceptual understanding of that? Let's go back to my corkboard image, okay? You got a piece of paper. You got thumbtacks. You got a pair of scissors, okay? Which is going to take the shortest amount of time to cut? 1, 2, or 3? And I propose it's 1, right? Do you see why I'm saying that? I've got 1 cut, that, and then I'm done. Over here, I've got to cut all this, go down, and then cut all this. Here, I've got to cut this and cut that, and then cut this and cut that. Does everybody kind of understand that? Because that one on the top left takes less time to actually cut out, the analogy that I'm getting to is that block shear path rips through less area than the other 2, okay? And think path of least resistance. If this failure path is offering less area to resist that load, then it's going to have a smaller VRN, right? I mean, how are we computing capacity in general? I know the block shear equation is complicated, but how are we computing capacity? We're taking some limiting stress and we're multiplying it times an area, right? Smaller area, lower VRN, okay? Does that make sense? Now, going to Mr. May's question, let me sort of explain why I didn't do the upper pass. In other words, here's the channel. why, okay, I've got bolts going like this. And this is enough for demonstration purposes. Why did I just do that? Okay? The reason why is you really need to take a look at what this channel looks like in real life. And that's, again, what I'm drawing, or what I'm about to draw, go to table 1.5, literally drawing what's right there on the top left corner of the table. I'm not, it's not really a magic trick. This is just replicating what's really already there. Okay, here's what the channel really looks like. That's probably a little wide. The channel looks like this, okay? So it's going like that. And I'm exaggerating a little bit, but I'm kind of getting my point across. The way channels are manufactured, the flanges aren't flat. They're actually sort of on an incline. The flange thickness that it reports in the manual is literally just the average, okay? Now, let me draw this in 3 dimensions, okay? Now, let me draw this failure path again. Okay? Here's what this channel really looks like. Something about like that, right? And I propose that it is easier, if I've got a connection like this or something like that, I propose it's easier to fail through that small little chunk of connection right here than it is to rip through that, sort of stocky part of the flanges here or here. I think this is the easier failure path than going on the top and bottom. Okay? Does that make sense? Okay. But I'm all about the isometric visualization. I want you to understand the thing in 3 dimensions. And the same thing would be true if we were looking at an eye shape, because we'd be ripping through both flanges as well.
Good job.
Thank you.
The only time you really worry about this other pass is if it's a plate, pretty much.
That, or if the bolts are in the flange, you know what I mean? Then it's a different story, because then instead of ripping through the flanges, you're ripping through all that web material. Does that make sense? Everybody else okay with that? This is good stuff, so this is the type of stuff I want asked, because I want this to be clear on Celebration. Yes, sir? Yeah, you can. Let me say this. More often than not, that happens in beam situations, beam bending, because what you're talking about essentially is a splice between beams. And when you splice a beam, we're getting into beam world, and I don't want to venture too far into beam world because we're not talking about beams right now. We're talking about tension members. Beams are being bent, and this is just being yanked on. But in beam world, the flanges tend to take most of the bending, and the web takes most of the shear. Okay? So when you splice, beams together, which they do a lot in bridge applications, you need bolts on the flange and bolts on the web. In that instance, the only thing that I would say is worth mentioning, at least for the purposes of this exam, is that your shear lag factor would be 1. It would be 1. And the reason why is because if you look, there's all these cases in the shear lag table, in table D3.1, right? But all those cases below are special circumstances. Really, the 2 cases that matter are case 1 or case 2. And case 1 says if every component of the cross-section is connected, U is 1. If only some of the components of the cross-section are connected, then you use 1 minus X bar over L. Okay? So does that make sense? Now let's be clear. Shear lag factors are trying to account for stress discontinuities. I'm not saying there aren't going to be stress discontinuities in an I-beam with bolts through the flanges and the web. Of course there are. But because the load is directly being transmitted to all of those elements, while we get stress discontinuities, we can essentially count on all of that net area being effective to resist that load. So that's why we take a U value to be 1 if we had the situation that you're talking about. Does that make sense? That answer your question as well? I will say I'll go ahead and tell you another one. We're not going to deal with any HSS sections on the exam, and we've haven't dealt with any HSS sections on homework or anything, you probably, I saw a couple people go, what? What's HSS? HSS stands for hollow structural section. It's basically tubes, like steel tubing. So square tubing, rectangular tubing, tubing. I'm not going to deal with that on the exam because the shear lag factors and whatnot that are associated are a little, I'll say a little unique, but really it's more associated with welds. And I'm not, we haven't even talked about welds yet, so I'm not really interested in those complications.
For shear lag factor for an angle,
Mm-hmm.
X bar, what would that be? Will that just be X bar or would it be Y bar?
It depends on which leg is connected. If the long leg is connected, it's going to be X bar. If the short leg's connected, it's Y bar. Because it's the distance from the connected face to the centroid. So it depends on which leg is connected. Now, as a follow-up, if you have an angle that has equal legs, like it's an L 5x5, it doesn't matter which one you look up because they're going to be the same. Like if you go find an L 5x5 angle and you'll see that X bar and Y bar are equal. So it doesn't matter. But for slenderness, don't use Rx, don't use Ry, use Rz. Principal axes, that Mohr circle stuff, right? Mohr circle stuff's fun, right? Remember that? Oh, you remember Mohr circle. Oh, yes, you do. You remember Mohr circle. Oh. My deformable folks remember Mohr circle. There we go. We got some head shake. There we go. All right, all right. Stress transformation, right? We'll be talking about that in concrete design in the not too distant future. So, oh yeah. Oh yeah. Don't worry, it's not so bad. Oh. Oh, great. We got plenty of time, so I mean, I want to exhaust any potential concerns. I want to go through them all. What? Possibly. What? That's possible. Yes. Yes. So if you've got a grid-like pattern of bolts, like rectangular grid, you're only going to have one net area, just, and then however many holes go through that section. If you've got a staggered connection, you're probably going to have more than one failure path. So literally through each failure path, just count up the number of holes that you're cutting through, and then it's just, if it's 3 holes, it's diameter the whole times the thickness. I will not give you a connection that has some bolts that are 3/4 of an inch and some bolts that are 1 inch. I'm not doing that because that's not done in real life. So I won't do that. I mean, I'm going to do my best to ground the exam in reality, No 4-inch diameter bolts. So. What's that? Well, you might throw them out the window for the exam. I'm not. I mean, these don't open, though. All right, you and you.
So for the lateral loads, or the wind loads or whatever, the K factor, this is on the homework. It's the first story is less than 15 feet tall.
Mm-hmm.
It's still like a 10-story building, but first story good by the.
Yes. Yes. Exactly. If you plot that KZ term, like KZ is like a parabola. So like if you plot it, it looks like this. Like that one on the top. Like as the building gets taller, it sort of like does this whole thing. But what we say is that if you're under like 15 feet, we say no, 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 no. We're going to have just a constant value. So KZ, if your story is 15 feet or under, use that constant value. Anything above, use that other one. So there's one that says Z over ZG and one that says like 15 over ZG, right? So that's the one that you'd go with if it's under 15. Does that make sense? And any of the other like associated parameters, I'll probably give you. Like I'm not just to make sure that you have them, like the ZG and all that. Did I answer your question? I'm sorry.
Yeah, I just,
Okay.
understood how to use it.
Okay.
Can you go over how to measure AGT and AGV?
The AGT and AGV. Okay. All right. The easiest way is to go back to this image right here. So, all right. So here's the channel, right? And it's being yanked on like this. Okay. So first off, when we're talking about AGT and AGV, we're talking about the paths that are inside the channel. So essentially this one, and this one, right? Makes sense? Because, I mean, the bolts are going to transfer that load to the members. So this is really what I'm interested in. Sound good? All right. The point really to look at is, see, this arrow is showing how the member is being loaded. I'm yanking on it like this. So I propose that this path right here is seeing tension, right? Like if I look at it, it's being yanked on. You know, it's wanting to act like a piece of taffy, right, like that. Now this is experiencing tension, but this path right here, these long paths, they're doing this and they're experiencing this thing. So they've got the shear going on. Make sense? So what I propose is this. All right, let me do my best to add a little bit more depth. See how I did that? How it's essentially going into the thickness? Okay, I propose, let me erase this shading a little bit so that I can kind of see what's going on. All right. All right, see what I've got going on there with the shading? I propose that this block right there, that is the gross area in tension, okay? Now, let me take this. See that? That makes sense, kind of? Okay, I propose that this blue rectangle right here, this one right there, I propose that is, oh, no, that's the wrong one. I got it backwards. My isometrics. You're testing my 3D art skills. I propose that this one, that is the gross area in shear. Does that make sense? But that is only half of it, right? The full gross area in shear, if I trace all that out, is actually down here. See what I mean? So for gross area in tension, it's going to be this length times the thickness. For gross area in shear, that length times the thickness times 2. Does that make sense? All right. We got time for maybe one or two more quick questions if anybody's got them. Yes, sir. What I'll say is this: you need to read the problem. I mean, I'm not saying that to be belittling or anything. I'm saying they might be and they might not be. So maybe part of it is to actually interpret and understand whether or not they're service loads or whether or not they're factored loads. What's also important is make sure that you understand that if it says service loads, those are loads that have not yet been factored. Okay? If it says factored loads, don't factor it again. Okay? Yes, yes. I will indicate very clearly if they've already been reduced, which, by the way, this is steel design, so don't worry about live load reduction. Concrete design, that's a different story, so, all right? Because concrete, we really cover gravity loads in there, so, yeah, I mean. Any other quick questions? How you feeling? You feeling good? You two feeling good? Yeah. I don't know much what I can do about it. How we doing, Mr. McCracken? You good? You good? You good? You good? I am sorry to hear that. It is February. You good? You good? You good? You good? You ready for the exam? All right. That's all I got. 8:30. 8:30. Be here at 8:30 on Friday.
I really don't know how I feel about that.
What does being sick in February? Like, how does
It's cold.
It's the winter time.
It's cold.